All right, so the warm-up, just a little refresher of what an exponential function looks like. So we have y equals 3 to the x, and making ourselves a little graph, plotting a couple of points. When you have a negative exponent, Colin, what does it do?
It like doesn't turn into a fraction.
Yeah, so 3 to the negative 2 is really 1/9, because it's 1 over 3 squared. So Colin, when you plug in a negative 1, a 0,
Just one.
1, and then when you plug in a 1, you get, and then 9. So when you have a negative exponent, it creates a fraction because that negative goes to the bottom, becomes a positive value. And then when we graph this, we have a negative 1/9 and, 1/9 and 1/3 at negative 2 and negative 1. And then up to 3 and up to 9. As I was walking around, I was trying to remind some of you, make sure you draw in the asymptote. There's always a horizontal asymptote in the graph. So this one here happens at y equals 0. That is part of the graph. So make sure you do have that drawn in your graph. They'll all have a horizontal one somewhere. The horizontal value changes if the graph is being shifted up or down. And that was the goal for the 8 graphs that you had to do by hand, just so you can kind of see, identify the differences why a graph shifts or how it moves. So it says, is this graph a function? Barry, is this graph a function?
Yes.
Yes, because it passes the vertical line test. The second question, is the graph 1 to 1? Dylan?
Yes.
Because it passes?
Horizontal line.
Right. So vertical line test and, that's supposed to be a T. And then the horizontal line test. And Dylan, if it's 1 to 1, will the graph have an inverse?
Yes.
Yes. So graphs that are 1 to 1 pass the horizontal line test, and therefore they have an inverse. So horizontal line test is a way we show that something has an inverse or prove that something has an inverse. It means each y has exactly one x, where a function, each x has exactly one y. So they're kind of opposites of each other. Any questions?
So B and C will always.
Yes, if you say yes to B, then yes, there's an inverse. Yes. They'll always go together. Other questions? Underneath it, just as a little reminder about inverses. Remember, inverses are found by switching x and y. So if you're switching x and y, the domain of f becomes the range of the inverse, because domain is your x, therefore it becomes the y in the inverse. It's switching, you're switching x and y. The range becomes the domain, or the y becomes the x in the inverse. So our regular function, the x, y values switch when we're looking at the inverse. I was trying to answer homework questions as I was coming around. Are there any questions I didn't get to answer? A lot of it was looking at a graph, looking at the table of values, looking at a chart, plugging in numbers just to kind of see what happens as the n value changes, the t value changes with time. Or the n value is the number of times something is occurring. So if you look below, in the little box, it talks about the log function. So an exponential function has an inverse, and its inverse is the log function. They go together, that's why we learn them together in the same chapter. It says the inverse of the exponential function with the base a can be written as f of x equals log base a of x, where a is greater than 1. So the base is this little subscript with the log. That base is the same base as our exponent. So, not the exponent, but the base and the exponent. So this base correlates with the base here as well. So this is called the base of the exponent. This is the base of the log, and those numbers are the same. So if they're inverses, those numbers are the same. again, in the little box, a reminder, the domain of the log is the range of the exponent, or the range of the log is the domain of the exponent. And that's just saying we're switching x and y. So we're going to see if we can graph a log function by using inverses. And then we're going to talk about some properties, and we're going to graph log functions by using the properties. We will not be using the calculator. So no calculator required, no calculator necessary. So underneath, we have the log base 3 of x. And we just graphed y equals 3 to the x, and I'm going to just pull down those numbers that Colin gave us. So we had 1/9, 1/3, 1, 3, and 9. So that was our exponential function, y equals 3 to the x. Its inverse is the log function, log base 3 of x. So the bases are the same. So they are inverse functions. So how could I graph the inverse function? That's doing anywhere. How could I get to graph? Yeah, we're going to switch the x and the y. So if these functions are inverses, I can graph its inverse by literally taking the same 5 points and flipping the x and the y. So now my x is 1/9 and my y is -2. So that's how you find an inverse. You flip the x and the y, switch the x and the y. And again, these are inverses. The bases are the same. So that's how you know that they're inverses of each other. They're related to each other. They have the same bases. So we're going to graph the 5 points, starting now at 1/9 and down at -2. So the x value is really small, where before the y value is really small. I drew in the original function as well, kind of dashed it in here. So this is y equals 3 to the x. You don't have to draw it, you have yours above. Just I don't have both of mine on my same screen. And now I have log base 3 of x. So besides inverses being found by switching x and y, what was the graphical property of inverses? Right, so they're a reflection of each other over the line y equals x. And you can see that by looking at both of them. Here is our original function, y equals 3 to the x, that's the exponential form. If I flip that over y equals x, it just kind of flips diagonally and I get this new function, my log form. So what is the domain of the log function? Josh, what would the domain of this log function be? Yeah. So it's going to start at 0. It's not going to touch 0. It gets really close to it, and it goes to positive infinity. That was the range of y equals 3 to the x. So now it's the domain. Josh, the range then, negative infinity to positive infinity. And again, that was the domain of my exponent. Because if I look at my exponential graph, it goes from negative infinity to positive infinity. That's the domain, so it becomes the range. What's the x-intercept? Here, what's the x-intercept here?
0, 1.
How about 1, 0? So x-intercept is 1, 0. Mine has it there, but I just didn't cross through. But I did have the point. How about the y-intercept? Carrie, what's the y-intercept? There is none. And again, that's the opposite. So my exponential function had a y-intercept, but no x-intercept. And then this one has a vertical asymptote, Carrie, at
0,
x equals 0. So now I have a vertical asymptote. Again, the asymptotes flip as well. So if I have a horizontal asymptote and I'm graphing the inverse, it becomes a vertical asymptote. This function is increasing, and it is 1-to-1 because it has an inverse. They go back and forth. They're inverses of each other. So if an exponential function has an inverse, the log function has to have an inverse as well, because that's what it means to be inverses of each other. So you can see they still have the same curved shape to them. It's still an increasing function. If it's increasing as the inverse, it's going to increase as its log. Questions? So we are going to review some properties of inverses, and then our goal would be to graph this without relying on the inverse and instead rely on the properties of logs. So if you flip at the top of the page, in the little box, is our conversion or our equivalency statement for exponents and logs. Because I can have one form and change to the other form and kind of go vice versa, back and forth, depending on what we're asking to do, what we're asked to be kind of like solving for. So at the top, it has the log equation that we just looked at, the log base A of x. So that's our log form. That is equivalent to x equals base A to the y power. So essentially, I'm switching my x and y values because I'm finding a true inverse. We have to switch the x and the y. It says the first equation is the logarithmic form, and the second equation is its equivalent statement as an exponent. So I have the log form. In order to write it as an exponent, the base stays the same, and then I switch the x and the y to get it in exponential form. So there are 3 questions here that are in log form, and you're asked to convert it to an exponent. When you convert it to an exponent, it should make sense. It should be equivalent when you're looking at the left and the right. So we have the log base 4 of 2 equals 1/2. Dylan, how would you write that as an exponent? So what would that look like if I have, this is kind of flipped. So right now we have log base A of x equals y. What would that look like as an exponent?
2 equals 4 to
Yeah. Does 2 equal 4 to the 1/2? What is the 1/2 exponent? Carrie?
the square root.
It's like taking the square root. So, Carrie, is the square root of 4 equal to 2? Yeah. So, this is still your base. Here's my base. And then these values flip-flop. So, my base is 4. And then we have x equals a to the y value. So, if you need to, like, rewrite the current form so that you can kind of switch it. So, the base stays the same. You're switching x and y. So looking at the next one, we have log base 3 of 1 equals 0. So log base A x equals y. Our goal is to write it as an exponent. So Lauren, what would log base 3 of 1 equals 0 look like? 3 to the 0 equals 1. Does 3 to the 0 power equal 1? Yes. Again, it should make sense. 3 to the 0 power is equal to 1. And then the third one, again, log base A of x equals y. Hannah, what's that going to look like as an exponent?
2 to the 5th equals 32.
Does 2 to the 5th equal 32? Yes, it does. So these should hold true when you're looking at them. The left should be equivalent to the right when you're writing it as an exponent. 2 to the 5th is 32. And multiplying 2 together factors. So the next group of problems want you to solve for x. So write the following as an exponent and then solve for x. So see if you can write them in exponential form. And if you prefer having the exponent a to the y on the left side, that's fine. So if it makes more sense for you to say a to the y equals x, but write them in exponential form and then find x. So Josh, how would I write log base 10 of 1/10 to the x?
10 to the x power equals 1 x equals.
There it goes.
X equals 2.
Why would it have a negative 2 exponent?
Square it to get 100 since it's negative.
Perfect. So he said if you square it, you get 100, because 10 squared is 100. To make it negative, or if you make it negative, that's how you get the fraction. A negative exponent makes it a fraction. So nice way of thinking about it. If you square it, you get 100. If you make it negative, then it's 1 over 100. Colin, how about letter B? How would you write that as an exponent?
3 cubed equals x.
So x is 27. Brenton, how about letter C?
X is 1 equals 2, so x equals 2.
The better just equals. Questions? Do you remember thinking these are really hard last year?
Yeah.
Yeah. Yeah.
Last year Miss Lucas taught us a way to
Like the little,
the
the
E and the L.
E and the L.
That's what
I just forget how to do
So it goes something like this, right?
Yeah, I feel like that's worse than.
Like the E, the X is connected with the Y.
No, it's
Yeah.
it's
Yeah,
A
it
to
goes
Y.
A
It's
to
A to
Y,
Y
it
and
goes
like
A to
Y
Y.
like X. So it like kind of made no sense.
So like it starts with the
Yeah,
10
we
and
should-
it goes to the
Starts with a 10.
yeah.
Okay.
And then you go to the
This
X,
is chapter.
Go to the
and then
X.
you round the E, and then that's the equal sign. So like
And it's an
10
E because it
X
changes it to an
equals-
X.
I mean, like.
Oh, 10x equals 1/10.
It's kind of confusing.
Yeah, I get that.
It makes
And
it
then you
makes
can also
sense.
go with an L.
And then you like go
The
through the one.
exponents with an X.
So
Like,
you
go
have the
through
3 and the 3, and then you have the equals and then X. Yeah. How does the L work?
You use them for the exponent.
For the next one.
Yeah, it's to change it to a log.
Okay, so if we look at the next one.
Yeah.
Okay, so how does the L work?
So you start the L, so go down to the 8,
Yeah.
like that, and then go across, and then go up, and then go to the 2, and then go up.
Yeah, that's what
So it makes like a blocked L.
Log
Yeah, it's just like-
So
it
log
was. So much more work.
8 64 equals 2.
Yeah.
Yeah.
I'm not like Van Gogh. Like I just wanna.
Hey, whatever works for you. So like I know Hannah said it's good. Gary said it works for him as well.
The calculator.
So if I make an L and then I cross, go over the equal sign and then come back up. So 9 would be my base. And then the 27 and then the equal sign and then 3 halves. Yeah, that works. Yeah. Again, if it works for you, great. If not, that's okay. If you can just convert it, that's fine. So my base is 10 over to the 0.001, then the equal sign, and then I would come back up. So 10.001 equals negative 3. What do you do for letter D? Emma, what do you do for letter D? You use ln. Remember, E is the natural base. The natural base goes with what we call the natural log. So we have the common log, the log, and then we have the natural log, except it's ln to stick with the log form instead of nl. So, Emma, how would that be written then? Technically, there's a little base of E down there. So it's still the E over to the L, then the equal sign, and then up through the 0. You don't have to write the base of e. It's assumed that when you use an ln, it's already there. And I know you're not allowed to assume, you're not supposed to assume. But anytime you use a natural log, the base is an e. So the natural log of 1 is equal to 0. You can put that in your calculator and check it out too. The natural log of 1 is equal to 0. Questions? So I think there's one more set of equations, and then we're going to look down at the graph. Nope, no more equations, I guess. Just those calculator problems. Oh, there's my equations I was thinking of. All right, so it says the natural log, y equals the natural log of x if and only if x equals e to the power of y. So those are the two conversions that go together. So anytime you have a natural log, it's with the natural base of e. And we talked about that natural basis. So I'm going to skip the calculator problems for now. Maybe we'll come back to them, but I'm going to skip over them. It really is just plugging in your calculator, either using the common log in your calculator or the natural log, those two buttons on the left side of your calculator. So just using one of those values. But I'm going to skip over them. We might be able to come back to them.
Yeah.
You okay skipping the calculator
I
problem?
like forget how to do that.
Impossible.
Which one?
Like I forget how to put like the bases. It's not.
Oh, whenever it's 10, it's already in your calculator.
What if it was like not?
We'll go over that on Friday. So literally, you're only hitting the log button. So you can put them in. Like, it's alright, we can do them. It's fine.
No, I'm good. I
No
just-
worries.
You're not in control.
So you're going to hit the log button in your calculator. I even have mine ready here. So you're hitting the log when the base is 10. Of course, my calculator's not going to work right now.
Okay, calculators is good.
There we go. So if the base is 10, you're just using the log button. And then was this 10?
Yes.
And then you just hit enter and you get 1.
What if it's
So
like 5?
if it's 5, then there's the change of base form, but we'll talk about that on Friday. There's like,
I missed that log of x divided by log.
yes, it's, so the change of base form. We'll talk about that on Friday.
I remember that.
So the ones you're doing today are just using these two buttons. So if you go down to letter D is the natural log of, is it a 2? 2.5. So then you're using the natural log. You're not worried about anything else. So it's either the common log or the natural log.
I saw it 2.
Is it just 2?
Yeah.
Oh. I thought it was 2.
Well, I saw 2.5 after that.
Okay.
What about negative numbers?
What about negative numbers? Which one is negative?
Can't do that.
C.
C.
Just can't do it.
You can't do it. What is the negative? What is it?
It's illegal.
Negative 2.
Negative 2?
illegal.
It is illegal.
Let's go.
Why is it illegal?
Because it's not real.
Because it says it's not real.
I don't know why it's not real.
Why is it not real? Let me
Oh,
go
wait.
back.
Because you can't take the exponent or the square words.
Yeah.
Yeah.
What's the domain of a log? 0
0.
to infinity. 0 is positive.
Yes.
So you can't have negative numbers because it's not in the domain. It doesn't exist. Is that where you were getting at?
Yeah.
Maybe? Any other questions?
One more.
No? Yeah. Yeah.
So if it's like ln and then e to the power, would you just put like second? Like
Yes.
ln
Here.
second?
Yep, and then, yep, exactly. Yeah. Good? Should be 2. Yep, awesome. Any other questions? Okay. So if you look at the top of the next page, there are 3 properties. The fourth one is kind of like an equivalency if-then statement. And we're going to rely on these properties to help us graph. And I want to kind of show you why the property works. So the first property says the log of any base. That's what A stands for, any base, any number. So the log of any base of 1 is equal to 0. This holds true because if I write this as an exponent, a to the 0 power, any number to the 0 power is always equal to 1. So as a log, if I have the log of any number, so maybe this was the log base 7 of 1, no matter what, that's equal to 0. Because as an exponent, any number to the 0 power is always equal to 1. So it's kind of like looking at it the opposite way. So it's a property, it's a fact. So if I have a 1 here, it's always going to be equal to 0. My second property says the log of any number of that same value is equal to 1. And again, as an exponent, if I wrote this as an exponent, a to the first, anything to the first power is the number itself. So 7 to the first power is 7, 10 to the first power is 10, 100 to the first power is 100. So it stays as the number itself. The third property says if you have the log of a base of a number to an exponent, then it's going to be equal to whatever that exponent is. And again, as a property, if I said a to the x, then that must be equal to a to the x. So here's my exponential form, the reason behind the log. So why the log property exists is because of the exponent. The last one is an if-then statement, and this is more of what we'll use when we start solving equations. But the log of a base with x is equal to the log of the same base of y. Then I can really just set y and x equal to each other and solve for them. So if the bases are the same and there's an equation after them, I can just worry about solving for the equation. So we're going to try and apply some of these properties, and then we're going to try and see if we can graph. So if you look, it says without a calculator. We're going to try and solve this couple expressions, simplify the expressions. So the log base 2 of x, the log base 2 of 3, if the bases are the same, then what could I say? Emma? X equals 3. And that's property number 4. So looking at the next one for letter B, the log base 4 of 4 equals x. Look at your properties. What is that equal to? Yeah, 1. And that would be property number 2. So property 4, and this would be property 2. These values are the same, it's equal to 1. If I look at letter C, I have the natural log of 1 over e. I'm going to rewrite this. How could I write 1 over e as an exponent? Harry? Yeah, e to the negative first. So if I look at that property, the natural log of e to an exponent is just equal to the exponent. So, Carrie, this would be equal to -1, yeah. Oops, I went the wrong way. So right here, it's going to be equal to whatever your exponent is. So when I have a natural log and an e to raise to an exponent, it simplifies to just the exponential value. So Carrie, that means letter D is equal to
2.
and letter E is equal to
0.
0. And then the last one says 2 times the natural log of e. What's the natural log of e equal to? Carrie? 1. So this is 2 times 1, which is 2. So I'm going to go through a graph, and then you're going to have 6 graphs to do tonight, and that'll be the hardest part of your homework. The problems in the book are easy peasy because it's just conversions back and forth, getting you used to converting. Looking at the graph at the bottom, we have log base 2 of x plus 1. We're graphing this without a calculator. We're going to try and graph it with the properties above. So we're going to make ourselves a little t-chart. The numbers we choose for x are going to be based off of those properties 1, 2, and 3. So log base a of 1 equals 0. Log base a of a equals 1. log base a to the x is equal to x. So these numbers here represent what we're going to choose for x. What it's equal to is our y value. So anytime a function is equal to something, that's our y. So if you look, I'll keep these up so we have them to kind of look at. My first x value. What number would I pick for x? Say it again. Not a negative one, a positive one. Because if I pick a positive 1, the log of any number of 1 is equal to 0. So I'm going to show you how to plug this in. So the log base 2 of 1, and then I have this extra plus 1. So I'm just going to put parentheses around this and then plus 1. So Colin, the log base 2 of 1 is equal to 0. And then I still have to add 1 to it. So this plus 1 is separate. So that's going to be 1. So I have a 1 and a 1. I've got a little bit of work in between. Okay, looking at my second property. If the base and my number is the same, so that would be property number 2. So if I have a base of 2, what number do I want to make for x? 2. So log base 2 of 2. Log base 2 of 2 is equal to 1 from the property, and then I'm also adding a 1. So I have the point 1, 1, and I also have the point 2, 2. So now the next one's a little trickier, because I need to pick the number so that it has an exponent to it. So what value could I pick of x that I could write as an exponent? Why could I pick 4? Yeah, so 4 is really 2 squared. So 4 can be written as 2 squared. So that means I have my exponent of 2 plus 1, that gives me 3. So I have a point at 4 and up at 3. And then can you pick one more value so that it would have a negative exponent? So if I wanted to have a negative exponent up here, maybe just a negative 1, what would my x value be if I chose 2 to the negative 1? 1/2. So if I had an x value of 1/2, it's really 2 to the negative 1. So log base 2 of 2 to the negative 1 means I have a negative 1 plus 1 or a 0. So my x value is 1/2, my y value is 0. So I get this curve. Those are going to be the trickiest problems for you to do. So no calculator, you got to use your mental math, and those 3 properties. I want 4 points for those. That last property should be used twice as a negative exponent and as a positive exponent. We'll probably go through some of those graphs tomorrow because they are pretty tricky. Your test, I'm halfway through grading the test. I have 25 done. I've got about 22 left to go. So as soon as I have them done, they'll go in Power School. So book problems should be easy. The worksheet after the notes, that's the graphs. They'll be a little more challenging.